Okay, so let me to start. So this my talk today will be focused on a single paper. This one, it's our recent paper, and I feel it attract a lot of attention from the community. And so, of course, great thanks to all my collaborators. This is our German, China, Sweden collaboration. But before, let's talk about general things, a kind of introduction. So this is a sketches of a simple skyrmion, let's say, and a simple hopfion, and topological notation for such kind of particle-like states. It is presented here in maybe a little bit unusual form, so it is very common in our community to write simply map between spheres, but this notation actually reflect more physics, because when we have, for example, skyrmion, in the most of the situation, it exists in real space, and in this real space, our sample is not in the shape of a sphere, but it's something flat, and that's why we actually map in one-point compactification of domain where skyrmion is localized into spin sphere. So this is what is happening, how actually the homotopy group works. And by analogy with hopfion, so if we have hopfion, so it's a localized state in 3 dimensions, and we can think that we can put it into some region which is gamiomorphic to a ball, and we can compactify this surface of this ball into a point. So this is the way how we actually get in 3-dimensional sphere and then map into spin sphere. So the major difference between these two textures, it is dimensionality. And the essence of this dimensionality, it's not being 3-dimensional, because we can take whatever 2-dimensional skyrmion and add thickness. So the structure will automatically be 3-dimensional. But 3-dimensionality of hopfion means being compact in 3 dimensions, and it automatically means mobility in 3 dimensions. So this is the major difference. And so actually there is a huge gap, approximately several decades, in mathematical society between full understanding of these two situations in abstract mathematical level. And today, so we will see how we can actually connect these two very different objects into a single magnetic system. So it is like we will help these characters living actually in very different world to meet each other and make a new world which is much more diverse. Yeah, so I have to give credits to Heinz Hopf. So his example of non-trivial continuous maps between spheres of different dimensions was a really breakthrough in topology in that time. And so it is the essence of classification we need. So it is not everything he did. So the third homotopy group finally was proven to have no other invariants a bit later after Hopf. So different people contribute to it, but his input, of course, it's the major one. Yeah, and of course, a famous Whitehead expression, which allow us to be to compute the Hopf charge and to identify the homotopy class with a certain integer number. So we have this explicit expression, and it is also a great result, and a very non-trivial mathematics is behind. So it was obtained by connecting homotopy groups with de Rham cohomology. So very non-trivial result for that time, and very useful. But very important thing I have to mention here is that this expression, like expression for the topological charge of skyrmion, for example, it doesn't work in back way. So what I mean, if we have some texture, so for every texture we can compute this expression. It will give us some number. So suppose we have 1, 2, maybe another number. It doesn't mean that we have hopfion. That's the point. So it doesn't work in the back way. So it's only consequence of homotopy group. So first of all, the condition for homotopy should be provided by the system. And if it is so, this expression have a meaning. That's important.
Question to this previous slide. So the Hopf invariant here, you start with 1 over 16 pi squared. If I remember correctly, you have 1 over 8 pi squared. That's right. Something missing?
It depends how you define this f. It could be a difference. So if you define it through the tensor, for example, an extra prefactor could appear. So 99.9, this is precisely, I'm almost sure. So that was very abstract level. It was about hopfion in whatever system in our imagination, let's say mathematical hopfion. Now let's go to magnets. So actually, to obtain a hopfion, it is issue. So I combined here results we have today, not all of course, but major, regarding hopfion stability issue. So the trivial approach, we can take expression, just a formula for magnetization field, which looks like hopfion, and substitute it to Landau-Lifshitz-Gilbert equation, right? So it will somehow evolve. So something will happen. But what will happen, it is necessarily lead to collapse if the Hamiltonian is usual Hamiltonian for magnets containing, let's say, exchange and maybe anisotropies. This is because of Hobart-Derrick argument, so we cannot have statically stable hopfion in such simple model. Yeah, but it of a certain interest, mathematical maybe, it certainly could be observed as a dynamical process, but not so far realized in experiments. Yeah, so that also interesting thing in study such kind of texture, it's zero fine damping. So if the damping is zero, so this hopfion with spin precession could exist forever, theoretically. Next. So this is just suppose we have an unusual magnet with competing interaction, maybe even stronger, up to frustrations. Then it could be shown that there is a room for hopfions there, not for everyone. So we have to find magnet where this competence is bounded in certain region, then it is stable. So actually it's a very old idea. So far we don't know any material, so it's not yet realized, but theoretically possible. Okay, the block C. So the idea is very straightforward. We can help stabilize hopfion by confining the hopfion in a geometry and fixing a certain boundary condition with extra layers or something like this. So the nice thing about this is that we have experimental realization of this idea in the famous paper by Peter Fischer group. But take in mind that by confining hopfion, we actually killing its degree of freedom for mobility. So, in other words, we paying for stability a very high price. So, in a certain sense, it is step back from three-dimensional to something less dimensional. And finally, it is another mechanism for stabilization. So it is enough to have bulk Dzelashinsky-Mori interaction, and in principle nothing else. And this result is an insight thanks to liquid crystals. So this video, it's from a science paper by Tai and Smaluk. And so why liquid crystal connected to magnets? This is because we have a very big overlap in the Hamiltonians, in the Frank-Cousin energy and Hamiltonian for cubic chiral magnet. And so this scenario, D, is not yet observed in chiral magnets, but so they definitely exist. So yeah, it's just difficult to find them experimentally, but I have no doubts they will be, they do exist and most probably will be observed, maybe very soon, but not yet. Okay, now let's go back to our result. And so this is actually, on one hand side, this is experimental confirmation that indeed we have stable hopfions in magnetic crystals. On the other hand, what we found, it was unexpected from the theory, because the hopfions we have, they are connected with skyrmion strings. And this is very unusual. Let's talk a little bit more about how we actually proving that we have hopfions. So this is example we have from experiments. One of the simplest one. So this is Lorentz transmission electron microscopy, under focus, over focus image. So we have a bright spot, which is, we know this is a skyrmion, and so some ring around it, which is of low contrast. And maybe it's not necessarily a hopfion, so how we can prove it? And so we do micromagnetics. And we do micromagnetics in very accurate fashion. So we try to account for whatever possible nuances. So if they have a thickness 190 nanometers, so we put in exactly the same thickness. So in the simulations, all the parameters are quantitative, and actually we did not feed the parameters. We took parameters from our previous papers, where these parameters were successfully used to describe a different phenomena, such as skyrmions and anti-skyrmions, skyrmion braids. They also good for chiral bobbers, and they are also pretty robust. So the numbers in the block B, so we can really change it, and the phenomena remain. But these numbers mostly affect the quantitative level. So this clip showing how our investigation process typically happening in the program. So, and of course, the demonstration of a single solution, the correspondence between single solution maybe can give some unambiguity. And that's why we did actually very extensive comparison between experiments and simulations. So we found a lot of different textures, and for them, we found the correspondence stable solution in micromagnetic model. So you can see here a lot of examples, and not all of them. So this is just a part. And so the pictures, experiment and theory, so they are fully quantitative. So fully quantitative. Yeah, so we, of course, always restricted to a certain sample. So making samples, it's time-consuming, it's a lot of work, etc. And it is difficult to check with very thick samples, for example, because of transmission electrons. It will be not enough, the brightness, etc. But what we can easily do in simulation, we can change the thickness in simulation, and we can track that the phenomena we discovered is indeed independent on the thickness. So this is indeed something general. So like in panel A, so we have this hopfion ring around skyrmion string for different thicknesses. So the panel A, it's fully quantitative with dipole-dipole interactions. And panel B is, in panel B, we actually go into the bulk, neglecting dipole-dipoles, and the phenomena still exists. So we can even reduce the bias field to 0. And so it's still, so it's very, very general. So we can have such kind of picture for only two interactions, exchange and Zelensky-Moria, and nothing else. So, and yeah, of course, there is mobility in 3 dimensions. So in the plane, all this structure naturally can show rigid motion. So the ring and the string just moving together. But in 3rd dimension, this 0 mode is a somewhat non-trivial, so we have a screw-like motion along the string. The interesting thing here, it's actually the remarkable thing, it's topological classification, and actually everything regarding topology is in this expression. So our task is to classify whatever texture, so whatever example from A, and it could be much more examples. We can imagine that we have a black box, and the only condition as we expect something the same on top and bottom side, and something trivial on the rest perimeter. And this is more general than classification applying to hopfion, because for hopfion we have to compactify the full surface of this box. But here are so the more degrees of freedom. So the top and bottom not necessarily trivial. So some texture can penetrate. And of course, we assume continuity for the textures. And so making long story short, we can compute this group precisely through certain tricks from algebraic topology. And the group turns out to be Z cross Z. So it's a set of 2 integers. And this is a abelian group of quadratic growth. It's very unusual, actually, for magnetism. So this is example. So the first case, we have 1 skyrmion, 1 hopfion, and the charges -1 for tube, 1 for hopfion. So looks okay. The second example, it's minus 11, and we have 11 skyrmions, so this is clear, but for Hopf charge, for some reason, we have 21. So what is the origin of this number? Yeah, so to explain this, we specifically designed a mathematical expression showing explicit homotopy. So this is not a physics, so this is an abstract level, just to show you what could happen if one will try continuously to detach, to separate Hopfion ring from the string. So in the top case, one can see that actually intrinsic topology of the Hopfion changes to the opposite one. So it's like addition a charge 2 to intrinsic structure of the Hopfion. And for bottom case, the Hopfion ring is the same, but there are two skyrmions. And what is happening, it's like addition of charge 2 twice. So every string contributes twice to the linking. And yeah, and so initially we have like intrinsically -1, then we have an intrinsically something like +3. So, but all these processes are purely continuous, and the topological charges are fixed. This is just to bring some intuition of what is happening. And this is in the language of pre-images, so we can compute using visualized tools the Hopfion charge by calculating the Hopf links between pre-images. Yeah, so actually there is a more predictive power from homotopy group. We can take a Hopfion ring and we can take a helicnoton. So helicnoton have topological charge, Hopf topological charge -1. So the ring have +1. And so we can check with our isomorphism to the cross product of integer that putting these guys together is equal to just skyrmion string. And we can compute this numerically. So we can combine these two guys together. And let's see what is happening. So now I move in this object towards each other to help them merge. So the process starts now, and look what is happening and how it is happening. That's the most interesting part. So the string is involved in the process. So, and at the end we have just a skyrmion string. So, and tracking this process confirm that there is no any singularities like Bloch points appearing. So this is indeed a homotopy. So yeah, the same we have expect, by the way, for liquid crystals. So for liquid crystals, the right guy is observed, the left one not yet. But in magnets we have the opposite situation, but these dualities should remain. So I encourage you to listen the talk by my friend and collaborator Nikolai Kiselov. So it's just he made it several weeks ago, and we planned to have a little overlap. So he really have in his talk different details. The details I not presented today about this our work. So already available on YouTube. Yeah, and so this is also fully quantitative comparison of holography images from very sophisticated Hopfion ring, around 11 skyrmions and some extra skyrmions from the side. So yeah, thank you for your attention.